How did you go? Did you go through the CNN Explainer website? Did you figure out what the commonalities are between, or commonality is between, the model that we built and the model that's running across here? We've got an input, a conv layer, relu, conv, relu, maxpool, conv, relu, conv, relu. Where have we seen that before? Well, I'll give you a hint. We replicated it here. Now, where they've got relu here, what we've done is we've just included it within our convolutional layer. So we've just set the activation here. If you really wanted to, you could also set it up as, where can we put it? We could put one here, TF Keras. This is how you might add an activation just on top. Activations, tfnn.relu. So that would be the same as this. So if we remove that, we've just got the exact same setup that we had before. But now we've just added in an extra layer. So I'll move that there. The trade-offs of that won't seem very clear now, but if you do need to separate your activation functions from your individual layers, you can always put them as their own layer. So just keep that in mind going forward. But that's all the difference is there. But otherwise, how exciting is that? You've already replicated a neural network that you found in the wild. And speaking of neural networks that we found in the wild, how about we see, just to demonstrate the versatility of neural networks in general, how about we see how the same model that we've built before goes on our different data set? Yeah, that sounds like a good idea. So in this video, we're going to see how we can use the same model as before. More specifically, the model we built with the TensorFlow Playground, playground.tensorflow.org. Is it .com or .org? We're about to find out, aren't we? There we go. Wonderful. So we can tinker with a neural network right here in your browser. Remember in a previous video, we built a neural network with 2 hidden layers and 4 neurons per layer. And then we made sure we had ReLU activation. We changed the learning rate. What was it? Atom, trusty learning rate of Atom is 0.001, and we had classification. But that neural network only worked with dots. Now we're working with a little bit more of a complex data set. We've got images of pizza and images of steak. But let's replicate, I'm going to have some more practice building neural networks. Let's replicate this model to see if it works with our image data set. How might we do that? So let's go here. Let's go set random seed. And then we'll put a little note here. Let's replicate the model we've built in a previous section to see if it works with our image data. And the model we're building is from the TensorFlow Playground. So I believe we can just copy this here. This is a beautiful thing about the TensorFlow Playground. That's a really long link. I'm actually going to get rid of that, and then I'm just going to turn this into a link. Wonderful. There we go. That should link to that model. So we'll set the random seed, tf random.setSeed. This is going to be an awesome test to see, first of all, compare the convolutional neural network to another style of model. Create a model to replicate the TensorFlow Playground model, and also be a good experiment to check the diversity of neural networks in general. We'll come back over here. Now we've got a little bit of practice building these dense neural networks. If I could get my cursor to the start of the line, tfkeras.layers. The first one we're going to need is flatten, because we need to reshape, or at least tell our neural network that the input shape of our data is actually now 224, 2243, because that's what our images are in. Remember, in our train data object, we can have a look here. Train data. There we go. Directory iterator. And then we can build our 2-layer neural network. tfkeras layers dense. There we go. For activation can be ReLU, and we're going here, tf.keras.layers.dense, 4, and the activation is relu. Wonderful. And then tf keras.layers dense 1 activation equals sigmoid. Now, how do we compile the model? So the beautiful thing about this is that we can just use the exact same compile parameters as above. Equals binary cross entropy. Beautiful. And the optimizer is going to be tf keras optimizers. Yes, that's a correct typing, not my own typing. Metrics equals accuracy. Beautiful. And then, of course, we're going to fit the model. We'll save it to history 2 equals model 2. Oh, getting ahead of myself there. Model 3 train data, because then we can pass it just the train data block that we've created before. And the epochs is going to be for 5, just the same as what we've done for our convolutional neural network. Steps per epoch equals len train data. And then we'll go validation data equals. So we want the validation data parameter here, as you might have seen, just gives our model a chance to train and validate itself at the exact same time. Validation steps, kind of like calling model.evaluate as training is happening. Beautiful. Now, are you ready for this? Is it going to work? Will our neural network, our new one, same one we've built before in a previous video, work with images? There's only one way to find out. If in doubt, run the code. All right, fingers crossed. Wow. This is going really fast. Because you know why? We've switched to a GPU hardware accelerator, and our data is already loaded, so it's just flying through these epochs. But its performance isn't doing too well compared to our convolutional neural network. Like, look at this. It's basically guessing on the validation data. And the training data is not doing too well either. But the good news is that we're failing fast here. At the end of the day, because our experiment is small, we've reduced our training data to only 2 classes, and we're only fitting for 5 epochs. That's only 40 seconds or so that we know, okay, something's wrong here. Our neural network, model 2, the same neural network that we've used in a previous video, isn't quite working with our image data. Now I want you to have a think about how might we upgrade this model or something else. Maybe we fit for longer, but I'll give you a little nudge here. Do you think fitting for longer is going to really help? Val accuracy has basically been a coin toss the whole time. So I'll give you a hint. We need to change this architecture in some way, shape or form. Do we add more layers? Do we increase the number of hidden units? I'll leave you to think about that until the next video, and what we'll do is we're going to upgrade this model to see if it can find patterns in our image data. But before we do go to that next video, I'd like you to give it a try. So take this, create model 3, and upgrade it in some way, shape or form so that it finds, we actually beat the validation accuracy of model 2, because a coin toss is, let's just say that's not going to cut it. So give that a shot, and I'll see you in the next video.